Right, so today's lab we'll be discussing spell checking. We saw during the last lab how we can build invert index using based on term frequency. So for each term, we build first the vocabulary, and from that vocabulary for each term, we will link all the documents that contain this term in our collection of documents. And for that, we tied our inverted index on terms that we use or we find inside our document, right? But sometimes if you use it, after when the user will type a query, we will then extract those terms from the query of the user and find off the posting that are inside our inverted index and return the associated documents. However, the user may not type like the exact query, or the query may contain typos. So in this case, our inverted index will not work because the term will not be found because the user didn't type the right term. So also search engine will integrate those spell checking or fix typos from a query before handling the query from the user. I guess before that, last time we, in the last lab, we were supposed to discuss also term frequency and also BM25 metrics. So let's quickly go through it and then we share the code. Can you please turn on the light? Thanks. Right, so here we are given like a list of documents. So we can say here we have, this is document 1, the second document, the third document, and document 5. So for this document, we want to find like a scoring function that will help us to assess like which document is most relevant for a given query. And the first metric that we use is TF IDF metric. So this function will compute the term frequency of the query that you have and multiply by the inverse document frequency. So this basically will find for you like the number of occurrences that a term has. Like if you have a query, let's say here our query is let's choose something like, let's choose something like insurance is similar. So if this is our query, we'll compute the TF-IDF for each term that is inside this query. So let's take the first term. The first term here is insurance. So for insurance, we want to compute the TF-IDF of insurance. For that, first we compute the term frequency, like how many times insurance occurs in each query, right? So for that, we just count. So here we have insurance 1 time, and we divide that by the total number of terms that we have inside the document. So for this document, we have 1, 2, 3, 4, 5, 6, 7, 8 terms. So the term frequency, let me just take this down. So the term frequency of insurance will be equal to, we have 1 occurrence of insurance divided by the total number of terms that we have from the document. This is for the document 1. Okay. And then we need also to compute the inverse term frequency, inverse document frequency. Why do we need that? We need this basically because sometimes we also want to account for terms that occur in all the documents. If you are looking for if you want to answer to a query, if a term occurs in all the documents, this means that most likely this term is not useful for the query that we want to handle. So we need to find a way to also cancel out those terms that are mostly present in all the documents that we have. So the inverse document frequency, which should be computed as the log of the number of documents that I have. I have 5 documents here. So here I have 5 documents divided by the number of times that the term occur in all the documents. Okay, so we have insurance only in the first document, right? We do not have it in other documents, so that will be equal to 1. So the final score, this shouldn't be there. Oops. Let me just write this. So the IDF of insurance is equal to log of 5 divided by 1. So finally, we have the TF IDF of the term insurance will be equal to 1 by 8 multiplied by the IDF, which is log of logarithm of 5, right? Similarly, we will compute the TF IDF of the other terms. So if we take the term similar, right? We will first compute the TF, the term frequency of similar for the first document. So we can see that we have similar here. So we have similar 1 time. So it's 1 divided by 8. But when we compute the inverse document frequency of similar, we will see that we have a logarithmic of 5 divided by the number of times the term occur in the document. So the number of documents that contain the term similar. So we have similar here. We also have similar here, have similar here, we have similar here, we have similar also here. Okay, so similar occurs in all the documents. We want to cancel this out because we will not contribute. These are similar terms as is, there, a, when, where, all these terms will penalize the score that you give to the final term frequency. So we end up having here 5 divided by 5 will be equal to logarithm of 1. So you have the IDF of similar, which will be equal to 1 over 8 multiplied by 0, right? So if you compare, you will see that, okay, for insurance here, you have certain value. You have a certain value, and for all the others, you will have 0. So for this particular query, for the query insurance is similar, we will also compute the term frequency of each similarly. And then we need to retrieve the document that we have the highest TF-IDF score. And you will see that the TF-IDF for insurance on the document 2 will be equal to 0 because we don't have the term insurance there. Same for all the other documents. So the document that we have the highest score is the first document, right? That will be written. However, the TF-IDF also suffer from a particular drawbacks, where if you have the term, for example, if you have the term doc, okay, in a document 10 times, okay, this means that most likely the document is relevant, right? But if you have the term doc in another document 20 times, okay, this means that most likely this document is more relevant, but it's not sure that it's most relevant than the document that is having just doc 10 times. But the TF-IDF will double. So if you have a document that contains docs 10 times, and you have another document that contains docs 20 times, the TF-IDF score will double. So this means that the TF-IDF is growing linearly with respect to the frequency. Okay, so if you plot it, you have, if here you have the score, and here you have the frequency. Okay, so basically it will grow like this. If here you have the term frequency. But does this mean absolutely that the document that contain docs twice as the document that contain only docs, like let's say 10 times? Does it mean that this document is two times more relevant than the document that contain docs just 10 times? Not sure. Okay. Also, the bigger the document is, if you have a document of bigger size, and you have a document that have like less bigger, if you have, most likely you have the term doc in the document that is bigger, more than the document that is having less size. But this does not actually mean that the document of bigger size is more relevant, right? So we need to come out with a metric that will also account for the size of the document that we are using. So that's why the BM25 will come in. So if you take a look at the BM25 formula, it's pretty similar to TF-IDF, but just it adds things that will account for the length of the document, okay? And also for the number of times the term occurs in all the documents. So if you take a look at this, you have this is for all the terms in the document. So you sum, it's a summation, right? For example, here if you have the query President Lincoln, the score will be equal to the BM25 President and Lincoln, that's summation. So for all the terms, we will multiply the IDF, the inverse document frequency, with this value, right? If you take a look, this is similar to TF, this is TF, and this is IDF, the same formula than before. But just it adds things that will account for the length of the document. So here, for example, in the denominator, we will take the size of the document and divide by the average size of all the documents, okay? And also for the TF-IDF, which is pretty similar. Here you have the term frequency, you have the number of documents, you have the term frequency of the term inside all the documents. That is normalized here. So if the term occurs in all the documents, this value will be higher than n, okay? So the logarithm will be close to 0 as well, okay? And what is interesting from this is that you also have these terms that are just constant, which mostly sometimes we choose k to be equal to 2 and b is equal to 0.25. These terms depend on the documents that the data set that you have. But generally, these two values are chosen. So what is interesting is that it will generalize the TF-IDF and also remove this problem where you have the biggest document size that will have more terms inside the document, and then the relevance score will grow like linear with respect to the term frequency. So in construct, we will see that for the BM25, it will grow something like this, okay? So we will not grow linearly. So we also account for the time where the document it's having bigger size. And then if the more frequent the term is inside the document, it will at a certain time will not give more score. So we try to be kind of constant. So that was what was missing from the last lab. But if you don't have any question, I will just back in the code. Have you implemented the BM25 score from the last lab? No? Okay, no problem.
Can you send like the lab same day?
Yeah, that was my mistake last time. I will definitely take care of that next time. So so I will update I'll update what I sent to you, and then you will take a look later on. So here's the implementation. You need the length, the total number of documents that you have inside your data set. You need the average length of the document. This is the total number of documents divided by the length of those documents. And then for each term, You just account for the term that are inside our inverted index. Okay. And then for them, you compute the IDF, which is, this is just the straight implementation of the formula of the BM25. Okay. You also get the posting from the inverted index. For each posting, you have the document ID and you have the term frequency. Okay. And then you compute the score, which is the IGF multiplied by the document frequency, multiplied by the parameter K plus 1 divided by the document frequency plus K. And then you have also the document length divided by the average document length. This is typically the formula that is implemented. And from that, you can then use the BM24 to score a given document for a given query. Okay. And then you return the document with the highest score. Well, this said, we will go to this lab very fast. So as we saw last time that when we are building inverted index, we have this issue that if I type the query with typos, okay, it may happen that the character or the term will just be ignored because it's not inside our term or inverted index. So we should find a way to fix the typos, okay, and then handle the query. So the first type of handling is handling wildcard. With wildcard, basically what we have is like, if I'm not sure about the spelling of a given word, but I know some part of it, I can insert wildcard, those stars inside the query. So yeah, so basically this can be handled using k-grams. Let me come back to the presentation. So basically this can be handled using k-grams. So let's say, for example, my query, I'm not sure about the spelling of my query. And I say, okay, my query is, I'm looking for something like something that starts with R and finish with ID. Okay, I'm not sure about what is here, but I know that it starts by this and ends by this one. Okay, and we want to answer this kind of queries. So this means that basically we need to retrieve from our inverted index all the terms that satisfy these patterns, right? And we do this using k-grams. So the k-gram would basically take a word and create all the k-grams of that word. If you're using 2 grams, we create 2 grams of that word. And for each of these k-grams, you will associate each k-gram with the word inside our dictionary that contains this particular gram. What does this mean? This means that, let's assume that this is our inverted index, where we have the term retired. And remember here, it's associated with the posting list, where we have the document associated, .2, etc. We have return, where we have document. We also have, let's choose return, like this. And we have document 3, document 4. And then we have also something like real, and so on. So for this particular query, if we just take this query as a single term, you will not find any term that match this. But since we want to handle wildcard, we will first create what we call the k-gram of that query. So from that query, we have the k-gram, we have this one and this one, right? And we can part this with these dollars, like it starts and ends by this one. So for each of these term, kgram that we have there, we create re, and then we will store all the words inside our vocabulary that contain this particular gram. So we have return, we have retired, return, and real, right? So for this one, we have another posting, which points on the list of the documents that we have inside our vocabulary, not list of the words that we have inside our vocabulary. So for that, we have retired, we have return, we also have return, and we also have real. For the second part of the term, we have ID. It does not match to the pattern yet, but it matches with one part of the wildcard. So we also at the end, when we retrieve to answer the query, we also make sure that the word that we have also satisfy the pattern. Okay. So, and then we have the second time, we have all the documents that have ID. So we have retired. Sorry. So we have retired, we have return, and that's it from the set of documents that we have. Let's assume that we also have another posting that contain let's say specify. Okay, so after building what this is what we call the kgram index. Okay, so after building this, we perform a Boolean operation on those kgrams. So basically, we are going to answer the query. We're going to answer this query. Oops. ID. Okay, so we're going to perform intersection of these two posting lists. Okay, and we end up returning this one and this one because they match here, right? And the others will be cancelled out. So after this, then we have the terms that are inside our document, right? And then we can use our inverted index that we had before. So we come in our inverted index, we choose this one, we choose this one, and then we access the document to return it. So this is how we can handle wildcard. Okay. Another way of doing so is not using wildcard, but spell checking. Okay. So if you have a given word that you misspelled a particular letter, okay, we need to find the word that you meant to write. Okay. So for that, we will use what we call the edit distance between two words. So if you have, for example, cat and dog, the edit distance between two is 3. So this is the amount of operation that we can make to transform the first word to the second word. Okay. So we'll see how we can implement edit distance to find all the words with the minimum edit distance. This means that if you have minimum edit distance, this means that most likely these words are very close to each other. Okay. And how? Yes, go ahead.
In the kgrams, how do we know which part of the word is missing?
How do you know which part of the?
Which part of the word is missing, right? Because
No, we do not specify which part is missing. In a wildcard, you said, I want to return something that contain. I don't know what is the ending, or I don't know what is in between, but something that satisfies this pattern. So we do not exactly want to return the part that is missing. Okay.
But in this example,
yeah,
the first one, but the query is like read, right? RD and ED.
Yeah.
So like you can it's misleading if we don't know which part is
This tells us which part is missing, this star. I mean, like, does it answer your question? Like, this star tells us which part is missing.
I know, but so is it specified before getting the query?
Yes.
Okay.
So this is our query. This is our query. Assume that's what is continuous.
Star wildcard, string only, it's not like operations or other things.
No, it's just specified, like as I written here. As written here.
The star symbol, the wildcard.
The what?
The wildcard star.
Yes.
The star in between. Does it represent all possible? Is it like what I mean is it like a character or two characters or strings or?
This means any.
So what if it's like words and spaces like RE, red?
No, these are anything starting with this and this without spaces. Yeah. Also, if you want, you can also type query, like if you don't know what the example that you have in the lecture, if you know how to write in university. Okay, sometimes you'll be Universitetskaya, Universitet, you just type like this. So anything that content start with university, and then the rest will be considered as the place that we should contain them. Okay. So for that, we will retrieve all the documents that have like university. Link them. These are from the Kgram, okay, and link them to the all the words that you have in your vocabulary, and then retrieve them. Yes.
Like for example, in university,
Yeah.
like, the missing part is at the end of the word.
Yes.
But like when we get the query, so we don't know which part is missing. If it's in the middle, so how do we know like which is like for example?
This is why we add this padding, where you have this to specify this is the starting point and this is the ending point. Okay, and any padding, any kgram that you have in between are just in between the word itself. Okay, and at the end we also need to make sure that the things that we have also satisfy the pattern. Okay, so for example, if you have, for example, red. If, for example, you have red, okay, if you extract the 2 grams of red, okay, you have those, but it does not satisfy the pattern itself. Okay, so at the end, you have one more step that we need to go to make sure that the words that you have satisfy the pattern that is given in the wildcard. Well, also these things, the data structure that is behind your inverted index is very important. Okay, so this data structure used for a hashing function, where you have the key, you hash to a particular memory address, and you store your posting list, right? Also, it can also be implemented using binary trees, because you need to retrieve information. But the problem with the hash table is that you need to also handle, like you can have very big vocabulary, and sometimes you have fixed size. You need to double the size when you have no more spaces in your hash table, for example. Okay. Also for binary trees, it's in log n, you can easily find like the term that you're looking for. Okay. So the data structure behind is also important for you to go through. So back in the lab, what you need to start, I guess you all have access to this notebook, right? Yeah, so let's get started by implementing several stuff. So I just show you what we need to do. So first, we need to build the original inverted index as we did before. You take the vocabulary, you extract all the terms that are inside the vocabulary, right? And then you build your inverted index. For each term, you associate the documents that contain this term, okay? And you also keep track the term frequency. And we saw that we are adding this term frequency as site information to avoid expensive computation later on when we want to use them. That's why we store the overall term frequency in all the collection. And for each document, we also store the term frequency for that document. This is the first thing to do. And then you need to build the kgram index. The kgram index is basically what? Is for a given query, you extract all the possible kgram, Okay, and for all this K-gram, what you do, you associate all the documents that contain the part of the K-gram, not the document, all the word or all the term inside your inverted index that contain this K-gram. Okay, and then you have to generate the possible wildcard options. So this basically reproduce the list of words that satisfy this wildcard. Okay, and also have to filter them out to make sure that okay, this list, each term inside your list also satisfy the wildcard. Okay, and then you can answer the query by taking all the words returned by the generate wildcard option and just retrieve the documents. And this is how you answer to a query containing wildcard. Okay. So the first thing to do is you have to implement inverted index from documents. Okay, you can do this from the last lab. You can use the same code. So go ahead and implement it. Okay, online, I'm using the free version of Zoom. So we will update the link in 10 minutes, in 8 minutes now. So you have 5 minutes to implement the built inverted index. was finished. So those who are online, if you have a solution, you can share your screen also with others. Does anybody have a solution? No? Who do not understand what we have to do? Okay. Who do understand? So you're not binary, right?
What is considered as a document?
Sure, it's a sentence.
Is it a sentence?
Yeah, you have a snippet here.
But it takes time to write the keygrams.
It takes time to write there.
To finish the keygram.
No, I'm waiting for you to finish. Who has done the built inverted index? Yeah. So here you have fact. In this page you have fact. Okay. So each line is a document.
Are we supposed to write this function without the organization has to be inside?
Right. We'll check if you recording. Right. So inside facts, you have the list of documents. So each fact or each sentence, it's a document. Okay. So you have to build inverted index. You have the list of documents there. So basically here you have for each document, you have also to index them. You have like aids of documents. If you enumerate all the documents that we have. So what do you need first from each document? You need tokens, right? And you can get tokens from different ports. And it be okay. So you can get your tokens from an input okay. So let's recognize the document and we lowercase everything inside. Okay. You can even filter them. You can filter them to keep just tokens that are not would not be accent or punctuation. Okay. So here we will can use lambda expression. So we make sure that is alpha of tokens. Okay. And then for each token, before these tokens, we can build a counter from the token. Okay. So we have a counter that we will do to counter in this token. So the counter will import it from collections. Yeah, this from collection. So for each counter that is, so you check if the token is not in our inverted index, right? What do? We add this token inside our inverted index. It depends, like inverted index. Yeah. Even without key, we loop inside the key. So you have like inverted token.key. So you initialize basically. As we said, it's a tuple. It tuples where the first term is the frequency. So here we have document. Okay, so here we can also have here the frequency. For frequency document in our counter, we can set here the frequency, and then for each document we have the document ID and the frequency of that term inside the document, right? Otherwise, what we do, we just increment the overall frequency of that document inside our inverted index. This means the term exists already. Okay. And then for the rest, we open that document inside our testing list. So we open this. And that's pretty much it. What's going on? Okay. So we can quickly check this. Fact. Impact menu values inspected. Okay, we'll change it a bit. Okay, if we get keys, so we have frequency. Okay. Cannot concatenate tuples. Which line is this? This should return integer, right? Count of token should be int. Why is it saying it's a tuple? Only concaten int. Let's see why it's.
You put the like tuple inside the list. Maybe that's the problem. Inside the if.
Inside the if.
Yeah, like you put the tuple inside the list. And when you want. You can just like.
Yeah, this is my inverted index. This is the term of the vocabulary.
I know, but like, I mean, the problem is, I think, because you're putting it inside the list, so you have to change the index.
The index of what? Which line?
At the line has your.
Yeah, inverted index of the token. Yes, I initialize it like this.
So, like in the else, okay, when you say like the first element, it's considered as a list. It's not a tuple because you define it as a list, not a tuple.
What I propose is remove the brackets of the first, so it should be frequency and I and frequency as a tuple because
Oh
I
yeah,
believe
You're
tuples
inside the
are
list.
immutable in fact.
Yeah, exactly.
And you might want to remove frequency when appending because you're already increasing it with the curve, is another thing with the previous slide.
yeah, this makes sense. We just append the tuple itself. Yeah, thanks. So, well, we have our inverted index built, okay, for each term. So next you will have to build the k-gram index from the inverted index. So this means for each word that you have in your inverted index, you build the k-gram of that word, okay? And then for each gram that you have, you associate words that are inside word of our vocabulary that contains this particular k-gram. Does that make sense? So first you have to define a function that will return all the possible k-gram of a given word. Right? Yeah. Have you implemented it? Build k-gram index.
No.
Okay, cool. Go ahead, 5 minutes, and then we will see the solution. So for example, if you have the word, say if you have the word food, and you want to extract all the 2 grams of this word, right? So the idea is we can extract this one, we can extract this one, we can extract this one. So you have food, you have O, you have OD. So if you are given a word of length n and k gram and k gram, what is the possible? What is the how many kg can you get from that word if this is the length?
Minus k plus 1.
Yeah, so you can get n minus k plus 1 kg. So that's what we do. So if we take the word food, and for food we create this, okay? And then we need the posting. In the posting, we add all the words in our vocabulary that contain FO, okay? So we add all those words, and for the next one, we add all those words, okay? We do it for each one. You can see that the kgram index can be very big, okay? Yeah. So if you, let me make sure I'm still sharing the screen. So if you want to return build kgrams of a given word and the value k, you should return what? You should return so you should return part of that word of I plus k, right? For I in the range length of what, right? Minus k plus 1, right? So we start from the first position, you extract the first gram, you slide, you extract the second one, you slide, you extract the next one, so you have extract all the possible kgram. Well, so now we have to build the kgram index from the inverted index. So you look through all the words in your inverted index, you build all the kgram of that word, okay? And for each of these words, you just find if there's a word or a term inside your inverted index that contains this particular gram. If it is the case, you add this to the posting list of that gram, okay? Till the end. So if the algorithm is clear for everybody, so we can just go ahead and implement it. So you have for, let's say for each token inside our inverted index of keys, what do? we need first to augment the token by creating a padding. So we have the start wildcard, the start word, plus the token itself, and plus the ending. Okay. So here you have the k-grams that will be returned by the function that we got, build k-grams of that. Let me write it like augmented token, and that augmented token and k. Okay. So this returns all the possible k-grams. Now for each of them, what do we do? So we check first if this particular k-gram, if it is already inside our k-gram inverted index, right? We take our inverted k-gram index of the k-gram and then we append the word. So we are building the posting list of that particular graph. So if it's not the case, we initialize our k-gram index with that particular word. And that's pretty much it. Yes?
Like add another condition for the sign, because we are looking after the k-grams, and like in the function for the build k-grams, it's going to take like the dollar signs in front of the letters, right? So it's going to be like k minus 1 gram.
What do you mean where?
Like
This function?
No, we add like 2 signs.
Yes.
Right? And when we like fit this into the function to get the k-grams,
Yes.
so it's going to like consider, for example, what is going to be the last k-gram of a word? It's going to be like a letter and the dollar sign.
Mm-hmm.
So it's going to be like, for example, if you have a bigram, it's going to be like that the last one is going to be 1 letter less than bigram. It's going to have like one letter instead of 2 letters, because one of them is going to be dollar sign.
Yes. So what's the issue?
So we have like, it's not going to be a bigram, right?
It's not going to be what?
Bigram, for example, like we have 2.
If you have 2? Like if you mean if you have only 1 letter in that particular dollar sign?
Yeah. Like, can I like write something?
Yeah, sure.
Let's say like we have so is this okay? But we have this.
Yes. Is that okay? This is just part of how your work is. So next, after building the k-gram, now we need to generate all the wildcard options. Okay, so you are given the wildcard, like this is the query. Okay, you are given the k-gram index, and you are given the inverted index. Okay, so from your wildcard, you need to extract the k-gram of that particular wildcard.
Excuse me.
Okay? In your k-gram index, you need to retrieve all the k-gram that satisfy this wildcard and performs the intersection. as we saw in the whiteboard, right? And then for each of these k-grams, you know the words that are associated to them. So the final intersection. So from the intersection, we can extract the documents that contain this particular word from the inverted index. Does that make sense? Okay, so you have 10 minutes to implement the generate wildcard options. Yes?
In the previous function, what is word?
It should be token.
Yeah, it should be token.
Which,
In
yeah,
the
yeah.
last
Yeah, that should be token, thanks. So this is token. So let me just test this while you're working.
Excuse me. Hello? Can you hear me? Hello?
Yes.
Can you please explain again what we have to do here?
You have the wildcard. This can be the query. It can be something like, as we saw before. It can be something like this. Okay. Or let's take our example. It can be something, let's say, okay. So from share, you have also to extract all the part of this wildcard. Okay. Yeah. So let's take an example more interesting. So if you have stu d no stu yeah. If you have something like this, and so if you have something like this, okay. So you have to extract. First, you take this. You have to extract all the grams that you have there. So since we built our inverted index with 2 grams, you also have to extract how many grams do you have in your inverted index. If there are 2, you take your query, you split them with the wildcard, okay? After splitting, we then build the k grams of each splitting. So if the size is bigger or equal than the k gram that you build your inverted index with, okay? And then for each of them, you then extract from your kgram index, you then extract those posting list of words that satisfy this particular wildcard. So you have them and you have to build an intersection. So this means that you want the posting list that have like ST, G, and S, for example. So you have an intersection. After intersecting, you will then have the list of kgrams that have like this word that contain all the information that you have there. Okay. And from the word, you can access them in your inverted index. And then you return all the words that are possible answer to this particular wildcard. Okay. And also, most importantly, you also have to make sure that it satisfies the value, it satisfies the regular expression with the wildcard. Okay. So there is a question in the chat: why do we have to add the dollar before and after the token? So this is just a padding operation. Okay. So we want to make sure that when we are performing the build wildcard, all our words are still inside the build index that we have, the kgram index that we have. Okay. So I want to make sure that when we perform the intersection, we're intersecting things that will definitely completely contain the total gram that you have from your query as well. Okay. So we also want to take account of the starting word and the ending word. So when we intersect, we will at the end we'll be able to ignore most of the term that contains like grams that are in between. Okay. So just imagine you have a gram that you have a thing that starts with WE. Okay. And then inside your, when you build your inverted kgram, you can have a lot of documents that have like WE in between. Okay. So when you're intersecting, you also want to account for only tokens or only grams that will also start by the given sign $W and ends by $W. So for the intersection, this is important. That's why you are padding. Okay. I hope that's clear for you, Hanan. So again, you have to update the link in 10 minutes. So, okay, so I will start implementing and you compare with what you have done so far, or anyone who has a solution, you can share with others. Not yet? Okay. How much time left? We don't have much time left. Okay. So first, from your wildcard, you have to augment. You have to augment the wildcard again with the $sign. So you have $sign plus $sign of the wildcard. Okay. And next, you have to split. So you have to split it based on star. Yeah.
I have a question.
Yes.
What if the real word has a star inside?
The star here is a special character.
Yeah, but what if the word like has a star?
Do you know any word that has stars inside?
Like maybe kind of emoji. Like I'm looking for. Sometimes people write words with symbols. It's not formal, but sometimes it happens.
Sometimes it has what?
Like symbols inside the words. Like just for explaining something.
You remember when we built our inverted index? We just keep words, not special character or emoji or anything else. Okay. So we are building this on top of inverted index. Okay. So we assume that these are special. This is like you're having regular expression and you're asking, what if I have like special character that is a regular expression pattern inside? It will just be examined as a special character. So you have the k-gram. So let's build the k-gram of our set. So what is the k-gram that we have inside our inverted index? We can extract it from the k-gram, okay? So we just get 1 k-gram and we return the size, right? So we can get the length of k-gram of 0 k-gram of 0 of what? So for each k-gram, you have the k-gram parameter. Yeah, that's it. So you have the length k, and when you have the length k from our splitted wildcard, we then build the k-gram of each part of splitting. Yes. Split, yes. Yeah. So next we need to update the k-grams. Yeah. So we have to go for each. Let's call this split grams. Split ways. So for each split, what do we know? We check the size. So if that particular part if the size is bigger or equal to k, what we do, so we add all the k-gram of that part inside our set of k-grams. Okay, so we will update this. Update this will build with k-grams of that particular split with k. Does that make sense?
Can you please explain again why k is equal to that?
Yeah, so remember we have keys here. We have keys there. So we need the value k of our k-gram that we have inside our inverted our k-gram index. Okay, since we have our query, we also want to extract all the k-gram of that query. So we need to make sure that if you are working on 2 grams, you also have to handle our wildcard with 2 grams. Does that make sense? Yeah, so that's why we extract k from the inverted from the k-gram index. And when you extract k, we then extract all the part of our wildcard. We also extract all the gram that we have there. When this is done, now for each gram, we have to extract posting and intersect those postings. Okay, so we have to get the postings. So we have for so for k-gram in grams, so for k-gram in gram, we have to extract the posting. So the posting is equal to, we get the posting from the k-gram index of that particular k-gram, okay? And then we add this. So when we want to perform intersection of 2 sets, it's always good to start from the set of the smallest size, right? You understand what I mean? So if I want to intersect two sets, I can start from the set of smallest size because it will definitely, the solution will not, will be at least that set of smallest size. Okay, because it is an AND operator. Okay, so we can kind of keep them sorted. Okay, also we want to make sure that we are taking the posting that can stand like the most occurrence of grams that we have inside our list. So let's call this sorted posting. So for each posting, we extract the posting, and in our posting list, we append the length of the postings, and also we put that posting there. Okay. And then we will sort this. Another question in the chat. Why is Bill K. Graham to update? Why is Bill K. Graham to update? You have it here. It extracts all the K grams that you have inside the document. Can you explain the idea of generate wildcard option again? So again, our generate wildcard option is you have the wildcard expression. Let me, maybe I can draw this very fast so that you can understand what's going on. Sorry, I was on mute. Maybe you tried to talk. I didn't listen to you. So what we will do is we are giving, for example, we are giving this query. We are giving the query. Let's say our query is do you have an example here? Yeah, okay. This is our query, okay? And this is, here you have our K-gram index. So the goal there is to return, you have this as a query. This is our query. What we did first we extracted all the possible K-gram that we can have. We said that we have RE and then we have ID. This is what we extracted from our query, right? We extracted all the K-gram. We are using 2 grams, okay? So we have this and this. Now we go inside our K-gram index, we find them, we have them here, okay? But we need to return all the possible answers to this wildcard. We saw that we can do the intersection. So we intersect and we see that we have this one and this one, okay? So this is what we need to return. The words inside our vocabulary that satisfy this wildcard expression. Does that make sense? So first, extract all the posting list. So we have the posting list, and then we intersect the posting list, okay? And finally, we return those words from our inverted index. So I hope this is clear.
So like there is no ending for any like right and the other word, like term, they're going to have the same, right?
We're going to have the
Same, no way.
Yeah, there's no waiting. Okay. So let me get back to trying. So we are here. We saw that we can sort them, okay, by the length of the posting list. Why? Because we want to perform intersections, okay? So we have the intersected posting, which is equal to a given set, okay? So now for now let's say so we can start here from the posting list of smallest size, right? So we take the first one, and then we get the first posting list. These are the posting lists, okay? So let's make the posting list as set, since we are gonna perform intersections. So the intersected posting list contains, so if I make this set, this means that it's already set. So let's just make it plain. So we extract the first one. So we are going from the smallest posting list, okay? And I'm going to perform intersection to growing posting list, okay? So we start here from range. We start from 1 to length of sorted posting list. Okay. So after this, we're going to grow this intersection posting list. So if you call set dot intersect of our current intersected list and the next posting list of higher size, because they are sorted, remember. So we take the first one. So we have the length here. This parameter will help us to sort by size of posting list associated. So after this one, we have the intersected posting list. So we have all the possible words that are inside our dictionary. Okay. So next, there's something that we need to do. We need to make sure that those intersections also satisfy the wildcard, that we have, right? So for that, we need to build a regex expression. For each correction, make sure that the correction satisfies the wildcard expression. So we have the possible corrections. So possible corrections. We start like this. And then for correction in our intersected posting, what do we have? We need first the regex expression. So if we take the regex as ra.compile, so we get our wildcard, and we make sure that each part should satisfy the should satisfy this regex expression. Okay, so we need to replace the star by a word and star. So for each correction, we check if the search of this pattern inside our correction, if it is not none, what do? This means that that word satisfied the pattern that we specified. So we open the correction. Okay. And from here, we remains with only all the word from our vocabulary that satisfy also our wildcard as regular expression. Does that make sense? Wait. And when we want to return, if you have several words, like let's say we have a list of words that satisfy this particular wildcard, right? The ideal case will be to sort them by number of occurrence. So if you have a given wildcard, but you have several of them, we can sort them by the number of frequency in the inverted index. Does that make sense? Because the hypothesis is that the more frequent the word is, the more relevant it is as well, right? So we will return it here, but sorted. Let's say sorted correction is equal to sorted. So we take for each correction. Okay. We specify the sorting as a lambda expression. So we take X. Lambda X. So when we take X, this means that we are taking it from our correction list. We need to see the frequency of this particular term inside our inverted index. So in our inverted index, remember, we can get X. And if you want the frequency of X in the inverted, in the given document, it is the first parameter. Okay, so this is 0. This is, we have the, how did we build it? You have, yeah, you have the frequency, you have the ID, and then you have the frequency, so it's 1. Okay, and then we sort it in reverse order. Reverse true. And finally, we return our sorted correction. So these are the possible sorted correction that we have. Does that make sense? So basically, that's the algorithm. We should get the intuition behind as well. How much time left do we have? -4 point. And then finally, we need to retrieve the list of document of facts that contains the possible wildcard. So you have the wildcards. So here we need to call this function generate wildcard options. So you have wildcard options. So we call the function that we specified before. What does we need? The wildcard, the k-gram, and the inverted index. So you have the wildcard, have the wildcard, you have the k-gram, and then you have the inverted index. Okay. And then you have for option in the wildcard options. What do? We get the posting list. So let's say we have doc IDs. So for each option, this is possible word inside our dictionary. So we can extract the posting list of that particular option. So we have index of option. So these are the postings. So and then we can get from, you remember the first term does not interest us, so we get it from 1 till the rest. So from here you have the postings. And from the postings, we can have the list of document IDs, right? So let me see if I can find it really quickly somewhere, and then we can test everything. So meanwhile, please record the attendance before we forget. Okay, so I will complete this and I will share the notebook with you. You have to test everything. So basically what you have to see is that for this particular wildcard, you generate the possible wildcard options, okay? And then you also search a document that satisfies these wildcard options. And then you can see that, okay, for this particular one, it will return all the documents that contain or that satisfy this particular wildcard. And then you have to handle also typos. The next.
Implementing the algorithm that we do.
What?
Just implementing the algorithms that.
Yeah. So next you have to handle typos on this particular case, where you have to handle context independent spell checking. Okay. For that.
So next lecture we will have a quiz.
You have what?
Quiz.
I guess, I'm not sure. I will check and let you know.
What about the next context?
The next context should be well. I'll also check and notify you in the group.
Thank you.
Like just give us
Office
the
hour
type
4
of-
PM.
Yeah.
Which room?
643 63 460.
460.
Yes. Online student, did you check your attendance, please? If not, write your email address in the chat.
I'm sorry. Okay, thank you.
Okay. Okay, thank you. Please keep sending your email address if you didn't check the attendance online.
Hi, Patrick.
I have a question about the assignment. I finally picked here.
Nice. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Okay, thank you. See you next week. Bye-bye.